Okay, let's start. I just think I need the microphone here. Hello, everyone, and thank you for showing up to this 5A session on offshore and renewable energy, coastal engineering and offshore applications. I have the honor of being both the chairperson and the first speaker of this session. So let me introduce myself. My name is Johan Roenby, and I am associated with my company Strømning and Rozki University. And I will just get right to it. So what I will tell you about today is a new algorithm that we have developed during the last 4 years, dubbed FloatStepper. And it's an algorithm meant to solve what is called the added mass instability problem, something we often see in coupling between rigid bodies and incompressible fluids in CFD simulations. So for instance, think of a offshore floating wind turbine like the one shown here. That's the kind of problem we want to work with. The method was dubbed FloatStepper because it was a product of a project called FloatStepper, funded by Innovation Fund Denmark, with the purpose of bringing floating wind from proof of concept stage to early commercial stage. And the way we want to do that was to develop new numerical models and also perform physical model tests. So the main partner in the project was DTU, Technical University of Denmark, and the model tests were done at DHI, former Danish Hydraulic Institute. And then one of the very interesting partners is Stiesdal Offshore Technology. They have invented this new floater concept called TetraSpar, which is essentially a tetrahedral steel structure that's ballasted with a heavy keel, also steel filled with concrete, and then hanging in these wires, I think around 80 meters down in the water column. So that has been sort of our case floater for this project. My company Strømning's role in this project has been to try to improve the 6 degrees of freedom fluid or hydrodynamics coupling in OpenFOAM, where we experience this added mass instability as quite a nuisance. Let's just jump into this, what this added mass instability is. So let's look at a very, very simple example here. Suppose we have a circular disk with density 0.5 and surrounded by a fluid which has the double density, and then we have gravity pointing downwards. Then if this is an ideal fluid and it's infinite, we can calculate quite easily that it should have a constant acceleration, which in this case should be a third. So it should just steadily increase its velocity upwards like this. If we try to do that with the current schemes in OpenFOAM, then what we, at least sometimes if we're not cautious, see is something like this. It's almost as if the body and fluid get into a fight and keep injecting energy into each other, and eventually the whole simulation explodes. This is the pressure field I show here. So this is an intrinsic problem, and there are methods to come around this in OpenFOAM. You can do outer correctors on your piezo loop. You can do acceleration relaxation, but these are sort of duct tape. What we want to do here is try to really solve the problem, completely eradicate the added mass instability. And we sort of looked into the algorithm and seen where exactly do we get, where does it arise, this problem? And I will tell you that now, and then also show what, in a nutshell, the FloatStepper method that solves this problem is. The main problem is this thing. So we take the Newton's second law, F equals m times a, and then from that we try to get the acceleration of our floating body as the force divided by the body mass. And that's wrong, we know from theoretical hydrodynamics, because we know that the force term here, it contains a lot of things. Let's call them F other, anything else. And then we have a term that's proportional to the acceleration, the instantaneous acceleration, and that constant of proportionality is what we refer to as the added mass. So if we are to plug this guy into this force into our Newton's second law and find properly find the acceleration, then what we find is that the real acceleration will be F other. So think of F other as anything but what is proportional to acceleration in our force term, and then divided by the body mass plus that added mass. So note that here, if we set the body mass to 0, then this diverges. Here it doesn't, because we have the added mass as well. So why don't we do this in CFD simulations? Well, that's because typically we do not know what F other and MA are. But in CFD, and that's the main point of FloatStepper, we can do whatever we want before we take our before we take our actual time step. So why don't we try to measure these two guys? And the way we'll do that is to first take a virtual time step, so not a real time step, with 0 acceleration of the body, and then measure the fluid force response. We will call that F0. That's just, in simple cases, just the pressure integrated over the body. Now, if we look at what we should get according to our equation 1 here, then we can see A is 0. Then this must, what we just measured, F0, must be equal to F other, so everything else. Okay, that's great. So now we got one of the quantities we actually needed. Then the next step is we take another virtual time step with some finite non-zero acceleration. Let's call it A tilde. And then we measure the fluid response force in this virtual time step. Let's call it F tilde. And then we can plug this into our equation 1. F tilde equals F other minus MA times A tilde. But here the only thing we don't know is MA. So if you isolate MA here, then we actually have the second quantity that we didn't know to calculate a proper acceleration. And then now it's just a matter of plugging these two guys into our acceleration expression, integrating that in time to get velocity and position of the body, use that to get for the boundary conditions of our fluid, for instance, pressure and velocity calculation. And then that is taking our real time step with a real added mass. So we have tried to implement this in OpenFOAM, and oh my God, did I learn a lot of programming by trying to do this. It's really hard to implement stuff in OpenFOAM when you're not a software engineer by education. But we sort of succeeded. How pretty it is, I don't know, but but here we have this light circle, rising circle case again, with a body ratio of 0.8. Remember, this added mass instability, it's something that kicks in when the body becomes lighter than the surrounding fluid. It doesn't matter if you have a stone falling in air or something. And then I want you to focus on the blue curve here. So what I show is, as a function of time, I show you the error we commit in acceleration, the relative error to the relative to the true expression we have here. And you can see it's basically constant as it should be, but it has an offset. But it looks much better than what we have with this 6-stuff rigid body motion library that we have in OpenFOAM. So the first one here, the yellow one, is, you see that this is a signature of these of the added mass instability, these wild jumps up and down. Can we improve it by increasing the number of autocorrections, which is a painlessly expensive operation? Well, we can sort of squeeze the acceleration or squeeze the oscillations in, but we don't get rid of them. But we do with FloatStepper. Now, regarding this offset, of course, that annoyed me. So I tried to investigate various things to see what could be the cause of it. And I ended up finding that actually in my simulations, I use an outer rim. It's not an infinite domain, obviously, but I have an outer rim which is 40 radii of the circle away. If I increase that to 60 or 80, then this offset is reduced. So it's actually not, I don't think it's an error. I think it's simply a matter of the body slightly feeling that it's in a finite domain, not in an infinite domain. So this is pretty promising, but it's all in 1D, and we need stuff in 3D. So a lot of the work we've been doing is to try to generalize this concept to 6 degrees of freedom. That has taken a long time. Now we have complicated coupling between the rotational and the translational degrees of freedom. I don't have time to go into all the details here. I'm happy to tell you about it after the session. But essentially, the concept is the same. We do a zero acceleration time step to get the zero force, and then we take not one but a number of virtual time steps to populate our 6x6 matrix, added mass matrix. So I'm just going to happily jump over this, and this is a teaser for anyone who would like to see it, talk about it afterwards. So we've implemented this in OpenFOAM and got quite sweaty, but this is basically implemented now, and we've come up with this really nice little test case, which is an elliptic body moving along the x-axis and then rotating. If it's in an infinite ideal fluid, then it should just move indefinitely like this, wiggling back and forth. You can see the theoretical black curve it should follow here. That's from the Kirchhoff-Kelvin equations. So we have something nice to compare with. And this is a nice case because we get this coupling between the translational and the rotational degrees of freedom. And you can see here the FloatStepper does a pretty good job in doing this. Now, this simulation is to sport that we can do this with zero acceleration. Oh, sorry, with zero body mass. So look, it says zero mass here. So this is a zero mass body. There's no gravity, of course, pulling it upwards. But that is just to emphasize that nowhere in the code do we take a force and divide it by a body mass. We have this F other that we divide by body mass plus added mass. And therefore, it works even for zero mass. I don't know how relevant that is to engineering application, but at least it's a way to show this sort of good stability here. And of course, we've tried to do mesh refinements on this case with various meshes here. I show the x-axis, the x component, the y component, and the orientation of this elliptic body as a function of time for 3 different mesh resolutions, and you can see it converges nicely to the black theoretical solution. So that's very nice. But this is an infinite ideal fluid, and actually the added mass that we continuously calculate for this particular body, it doesn't change with time. What's really getting interesting, that's when we start to get when we have a body that's near a boundary or near a free surface. Like for instance, here we have a wave flume with waves generated here on the left and a body floating freely. And then it's hit by a big focused wave. And as the surface of the water changes, and even we have green water on the body, the added mass of the body will change because of this change in the surface shape. So we need to continuously calculate the added mass in this kind of simulations. And we have done that and we do that in our FloatStepper algorithm. And we have validated, we actually, it's difficult to find really good validation data, but luckily as part of the FloatStepper project, we got a physical model test made at DHI with this tetraspar concept. So it's Siddiq Aliar from DTU who did these simulations. So again, a wave maker boundary condition here. He also implemented Moordyne coupling with the FloatStepper algorithm, so we can get some realistic mooring lines. And it seems to work pretty well. So here I show you the surge. So that's back and forth, heave up and down, and pitch of this tetraspar, showing experiments in black and FloatStepper results in this orangish color. And mind you, it's not a perfect match, but we also have the complication that we have mooring lines where we need to adjust the parameters going into their stiffness and other parameters. So with that in mind, I think these are pretty promising preliminary results. So with that, I just want to say that in summary, we have come up with this concept, which is a new way of coupling rigid bodies and fluid. We call it FloatStepper. It's we think it solves the added mass instability period. But that's up for you to test, and you can do that by going in. This morning I got it uploaded to GitHub, so you can go in there and give it a try. But mind you, this is bleeding edge, meaning that you should expect, and I also expect you to report whichever bugs you find in the code. I hope this is sort of the start of some good collaborations. At least I'm very interested in hearing how you work with fluid or rigid bodies, and to what extent this is a nuisance to you, these added mass instabilities. So thank you for the attention. And this is just the FloatStepper, the TetraSpar concept with real people standing next to the quay here, just to show you the size of these fantastic structures. Thank you very much. So, questions? So the question was, where is the algorithm implemented? And the answer is that it all started with a copy of 6 rigid body motion, copied and then modified during 4 years. And then what we came up with is this. So you will recognize the code structure from, if you are familiar with 6 rigid body motion, then you'll recognize that. It's also, in code structure wise, it's similar to rigid body dynamics, the other multi-body version. So yeah. Other questions? If other can be, it can be gravity. It can be your mooring lines. Actually, added mass. When you look at the Kirchhoff-Kelvin equations for theoretical hydrodynamics, then these are equations that show you the forces you have due to added mass. And there are some things that are proportional to accelerations. That's the ones that we have in MA times A. But there are also some terms that are not, that are just proportional to the velocity, and they would go into F other. So anything, you should just think of F other as anything that's not proportional to the acceleration. Lump it all in there. When you say 1/3, you mean that the acceleration was 1/3, or what? A third? Oh. I think, yeah, is it this 1/3 you refer to? Yeah, okay. So this is the theoretical value you would get for the acceleration in ideal fluid. And you can see that here in the denominator we have rho B and we have rho F. And if you just ignored added mass, then you would not have rho F down here, and then you would not get a third. In fact, if your body was very light, then it would go to infinity. And a very curious story here is that there's a brand new version of the Fertiga, of the numerical methods for hydrodynamics book by Fertiga and Perich, and they actually have a new section where they forget this term. So I was a little, I know this. But yeah, did it answer your question? Yeah, yeah. It comes out. This term comes out from integrating the pressure over the body. Yeah. Okay. I think we need to move on to the next speaker. Let's thank the speaker again. And our next speaker is Mohamed Rozki, who will speak about impact forces of a bore-driven swash over an overtopped obstacle. Sorry, there was an error. Will you help with the presentation?
So, hi everyone. I'm Mohamed Rozki. I'm a PhD student at the SIAM laboratory at the University of Po and other countries. So as you can see here, we have collaboration with lots of companies and also local authorities. So my main talk today will be about impact forces of a bore-driven swash over an overtopped obstacle. So just to show you the outline of my work as displayed here, I will start with the context, then with the approach, speaking about the analogy between bore propagation and dam break flow, then showing the different phases of dam break from generation to impact, testing the sensitivity of impact parameters like force and pressure, for example, to turbulence models, K epsilon, K omega, and K omega SSC. Other models are also studied, like the K omega SSC modified models by the Boulder and Furman 2018, but not shown here. And also the laminar case, showing the results. What are the real discrepancies found regarding the impact parameters, and finishing my talk with a conclusion. So our team in France is mainly working on storm impacts on structures. And as you can see here in the South Aquitanian coast, in this top left panel image, you can see that in this old Bay of Biscay, lots of spots like this one have been subjected to really heavy storm impacts. This is the reason why local authorities have thought about like a protective solution that can be put when a storm warning is issued. This is why they tried to raise this warranty level by putting this removable dike made of sandbags. So as coastal engineers and also as CFD engineers, the question is how we can design this kind of structure. And we don't find lots of reliable answers in the literature, in the scientific literature, but also in other guidelines like the overtopping manual, for example. This is why in our team, we want to understand more what are the dynamics, the impact dynamics happening in this kind of structure, in front of this kind of structures, especially in storm impact. So as you can see here in these two images, this is the Grande Plage of Biarritz in southwest France, where we have two cases. The first case is where this building is impacted by this very heavy storm, these very energetic waves. And in the first case, we didn't put this removable dike, but in the second case, we put it. And you can see that waves can really overtop. Actually, they are not waves. They are broken bores that are transformed into swash flows that are overtopping this kind of pedestrian promenade. Then they can potentially impact this structure behind. And in this second case, we can see that this removable dike is damping actually the forces that can be applied potentially in this downstream structure. So what we want to do in our laboratory is to try to understand very finely what are the impact dynamics happening in this kind of structure. But we know that the real case scenario is very complicated because the physical processes involved are very complicated and are interacting between each other. So we have wave break-in, we have also this bore-bore interaction, as you can see here. So this bore is interacting with this other one. We have also this rundown because waves are not always going in the direction of the seawall, but can come back also. So we choose to simplify the problem to a dam break flow because the analogy between the bore propagation, turbulent bore propagation, and the dam break flow over wedge button is reported a lot in the literature. And we simulated this beach, this mild sloping beach by this slope that you can see here. So this bore will go, collapse, create a swash flow that will after impact, then overtop this obstacle. So you can see here the 6 phases of the flow. So we have a gate actually here that is lifted instantaneously. So like in 0 seconds. We also use this 6 DOF motion actually to use this overset method to lift the gate analogously to the experimental work. But in this case, we choose just to show you the simplest case where the gate is there is no gate actually, where the flow just propagates directly after the beginning of the simulation, creating this bore with a turbulent front, which will propagate, then collapse on the slope, creating this very tiny water layer and very rapid water layer, this swash flow that will impact in these 2 phases. So in the first impact phase, it will be an upward phase and then a downward phase when we can see this free surface reconnection then creation of an air cavity, and then the movement of the flow to the left. So yeah, I have also to say something, because in the normal case, this removable sandbag is movable actually. So this sandbag units can be displaced. So normally you should put a dynamic mesh, which is the case, which we did actually. But here we are showing you the simplest case to really concentrate on the impact dynamics. So we know that this flow is very turbulent, that we have free surface reconnection, and that the flow is very aerated. This is why we used the multi-phase solver interform. But the question that we asked ourselves in the laboratory is, how sensitive is the impact parameters, so forces and pressures, to turbulence models? So to address this question, we are showing here a test sensitivity test to these three turbulence models, to the classical ones. So the K epsilon closure, which is very accurate far from the walls, the K omega closure, which is accurate near the walls, but which is very sensitive to the free stream turbulence values, like K, for example, the turbulence kinetic energy, and the K omega SAC, which is a combination between the two models. So a model blending between the K epsilon far from the walls and K omega near the walls, with this blending region between the two of them. So what we found is aligned with what was reported in the literature. For example, in the study of Liu et al. Of 2022, we found that when this swash flow is advancing and hitting the bottom of the obstacle, so these four pressure probes colored here, red, black, light blue, and the purple one shown here, so show the pressure evolution. So in the case of impact, we can see that the impact firstly is very impulsive at the bottom. And we can see that the order of magnitude of the first peak and the second peak are very different. So there is a very big difference between the two first peaks on the bottom pressure, for example, which is not the case when coming up towards the obstacle. For example, in the black one, we can see that the order of magnitude of the first peak and the second peak are quite the same. This tendency is inversed in the two last pressure probes, where we can see that there is a second peak much higher than the first peak in these cases. As for the force, we can see there that there is an impulsive first peak here. Then there is a secondary peak happening at the downward phase of impact. When we see that this wave is reconnected, creating this air cavity, there is an increase, a very fast increase of pressure at the bottom. And we can see that we found a very, very big secondary peak in this case. So using the K epsilon closure, we found that the second peak is higher than the first peak, which is aligned with the literature. Using the K omega closure, we found the same tendency, but we found that this impulsive peak in the first case is much lower. That's what we found in the using the K epsilon closure. And we found also that this second peak happening after the closure of this air cavity is much, much bigger than what we found using the K epsilon model. Using the K omega SAC model, we found that the first impulsive peak didn't happen exactly at the beginning, because the water jet was very aerated and lots of areas of the field was touched instantaneously at the first stage of impact. We saw also that there is two peaks of impact. So the first peak and the second peak have quite the same order of magnitude. And using the laminar case, we can clearly see that the results are very different from the cases using turbulence closures. And there is a very big difference between the first peak and the second peak, where the second peak is much, much higher than what was reported in the three previous cases. So now confronting all these force impact peaks, so these first peaks at the upward phase of impact, you can see that there is very big difference between all of them. For example, between K omega SSC and K epsilon, we can see that we have an RMSD of 34 Newton per meter. We have an RMSD of nearly 49 between K omega SSC and K omega. And it's also the case between the turbulence models and the laminar case. So the question is why we have all these discrepancies regarding this pressure field, especially at the bottom, and also the force. So we tried in the four cases to correlate the impact force, but also the pressure at the bottom with some flow properties, like for example, with the flow front velocity and the front slope. And what we found is that different slope is the deterministic parameter, because we found nearly a perfect correlation between the bottom pressure peak and the front slope in each case. So now in the downward phase of impact, we found that there is big discrepancies between these peaks. So as, for example, between K epsilon and K omega, we found a 67 Newton per meter discrepancy, a big discrepancy between K epsilon and K omega SST also, and it's also the case for the laminar one when confronted to the turbulence models. So now to recapitulate a little bit what we found regarding the second peak impact when plotting the force with this water height, with this elevation of the water jet, we found that here, this second peak is corresponding to the stabilization of this water jet at the downward phase, which is in accordance with the findings of Lui et al. 2022, who found that the second peak is corresponding to the creation of this air cavity that you can see there at the downward stage of impact. So what we want to say here is just as coastal engineers, we are we generally think that the displacement of removable dikes is created by this first impulsive impact, which is not the case as we see here, as the second peak is much larger than the first peak in the three cases using the three turbulence models. Yeah, so to conclude, what we found is that each turbulence model closure captures the bore-driven swash flow impact phases. So the fifth phase and second phase and sixth phase, which show the upward and downward phase of impact. The forces and pressure are highly sensitive to turbulence model closures. The second force peak is greater than the first one, which is already reported in the literature. The first peak of bottom pressure is almost perfectly correlated with the flow front. So what we will do now is to perform more in detail a mesh sensitivity test, because we already did one and we are using a 2 mm mesh here in this case, and we have a Y plus of nearly 5. We are setting a dam break experiment to measure these pressures and confront it with our findings using this three turbulence model. And we want also to investigate more in detail, very finely, what are the reasons behind this sharp rise in pressure after the closure of the air cavity. So thank you.
Thank you for the presentation. Time for questions. We have one over here. Can it maybe?
Hi. So personally, I'm particularly interested in the meshing. Is it possible that you show the mesh of your website? Or maybe you can just tell, like, what did you use for meshing? Did you use an automatic mesher? So mesh, block mesh, and you just refined manually, no automatic. Snappy hex mesh. Okay. Thanks.
Any other questions? We have plenty of time. Yeah, please. I mean, we have plenty of time, so okay, you're happy. Okay, so
So the reason why I have so many questions, because in my company we also work with water, and we face like functional challenges every day. And even though we do rather pipes and you do rather waves, still I think the models and the physics are quite similar, and that's kind of the reason. So so for example, so I'm just curious, like what surface tension models did you apply? A little loud.
We're capturing the. Me too. We are capturing the free surface using the VOF. Is that was your question? VOF, volume of fluids.
He was asking about the surface tension modeling what kind of surface tension back then.
What I didn't get the point. Yeah. 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 Okay, I get you. Yeah, there is interform. Yeah.
Sorry.
Okay. Okay.
Maybe I can add that usually we do not resolve small bubbles and droplets to the sizes when we're doing waves. We don't resolve them to the extent where we can set a meaningful surface tension. There is a surface tension parameter and constant/transport properties, but it doesn't make sense for this kind of well, unless you have a really fine mesh, but I don't think you do. Yeah, okay, then it could be actually, yeah. Mm-hmm. Can you? Yeah.
Have you thought about using LES modeling?
No, because we want to use what we are doing now in operational applications. Because we are a little bit scared that the computational time will be very large. This is 2D, yeah.
Let's take the speaker again. Move on to the last speaker of the session, who is Guillén Campaña-Alonso, right? Right.
Okay. Yeah. Well, like that. Yeah. Okay. Thank you very much for coming. My name is Guillén. I work in the wind department of the National Renewable Energy Center of Spain, and I also started my PhD in the Universidad Politécnica de Madrid. So in terms of the European Green Deal, increasing the offshore wind energy production will be essential to face the climate change issues. But what is offshore energy? Offshore wind energy is the one generated by the wind turbines that are located in our seas. Why go to the seas? Because we have better wind resources and also more capacity of installation. But our coasts are too deep, so we need to use floating offshore wind turbines, which are a novel technology that is which is represented in the image. It is composed by three main elements: the wind turbine, the floater, and the mooring system, which is not represented in the figure. And we have 6 degrees of freedom for these structures: charge, sway, heave, roll, pitch, and yaw. Okay, there are many challenges for this technology, and I would like to highlight some of them. The industry right now needs of reliable tools to estimate adequately power production and load estimation. We need to understand the structure as a whole, not as a sum of 3 parts. So we need to start facing the design in a co-design way. We need to understand the floater and wind turbine interactions. One of the key points of the for the owners of the wind farms and the OEMs is how the annual energy production is influenced by wind turbine spacing and wind turbine displacements. Another one issue that it is important to resolve is how the floating offshore wind turbine interacts with its wake and with nearby wakes. So we in FENER, we have developed a tool which is called OF2, which is based in the coupling of OpenFOAM and OpenFast. OpenFast is a tool that is usually used on the wind energy for analyzing the, the wind turbines. So in each time step, what we do is we model, we model with OpenFOAM the floater, having a good solution for the hydrodynamics, and we use the OpenFast to model the wind turbine, and including by this way the control system and the elasticity of the components. So in each time step, we get the platform position, velocity, and acceleration. We pass it to OpenFast. OpenFast do the calculation, integrates the loads at the tower base, and these loads are used in the library rigid body motion to determine how the wind turbine will displace. By this way, we obtain a computational cost reduction because we are not solving the wind turbine. We do not need a fully resolved approach on the top of the floating offshore wind turbine. This approach has been verified in a paper that has been accepted for publication, which is called Coupling OpenFast and OpenFOAM for High Fidelity Aerohydroservoelastic Floating Offshore Wind Turbines Simulation. Here we can see on the left figure, we can see the platform pitch displacements, and on the right, the platform surge. This is a quite simple case, and we have a good agreement between the OF2 tool and the OpenFast only simulations. This way, using OF2, we can overcome some limitations of the current model implemented in OpenFast. We also can obtain the pressure distribution that could be used to improve the designs, to optimize the designs of the platform. But aerodynamics are only modeled in OpenFast, only in OpenFast. But the reality is that we have wakes, and exists interaction between wind turbines, and this cannot be modeled with OF2. So we need to look for further solutions. If we look to the wake structure, we can see how the vortex are generated at the tip and at the root of the first rotor, and the flow is modified for the downwind rotor. We believe that this can be solved, and the tool, or that OF2, can be improved if we use an actuator line model and an actuator line approach to model the wind turbine. The actuator line model, what does is to discretize the blades and model them as a series of actuator points where the wind speed is measured and loads calculated, and introduced in the Navier-Stokes equations as source terms. For these cases, we have used TURBINES, which was developed by Pete Bachand and his team. Okay, to test how the turbines from library work, we modeled an scale version of the DTU 10 megawatt wind turbine. We measured at this series of points, which are located 2.3 diameters behind the rotor, the wind speed. We have performed mesh sensitivity analysis with 4 meshes, which they all follow the same structure. We have 3 refinement zones, one with the final refinement, which is on level 4, which is located surrounding the position of the wind turbine. The number of cells ranges from 400,000 to 9 million cells. What we are now to compare is the force distribution in the x direction of the blade, which is responsible for the thrust of the wind turbine, which will make the floater move backwards and forwards. And also we will compare the wind speed at those points that I told you before. We see that when we refine the mesh, we obtain the convergence of the load distribution, and we also can visualize how it affects to the representation of the vortex that are shed from the root and the hub of the wind turbine. But actuator line model requires from some corrections at the tip and at the root. This is not required by fully resolved meshes. Here there is a comparison between an actuator line model with both corrections at the tip and at the root, which is in blue, We have represented also only with root corrections and also with no corrections. Okay, if we look to the wake, the wind velocity at the wake. Oh, sorry. What we can see is that if we use no corrections, we have some over prediction of the loss. This is also collected in the literature. And we can see a greater deficit on the wake if we use no correction. We have also compared these results with a fully resolved approach. The hub presence is the main difference on the on the hot wave measurements. We can see that there is a greater deficit due to the modeling of the hub. In the fully resolved approach, the geometry is meshed as it is, but in the actuator line model is represented as an actuator point. If we look closer to the force comparison, we can see that there is a good agreement in the main part of the blade, but differences arise when we go to the tip. But I do not want to withdraw any conclusion about this, because we use a snappy mesh, and a snappy hex mesh always struggles with aerodynamic shapes, and the tip of the blade was not properly meshed. If we do not model the wind turbine, what we can obtain, or what we can afford, is to perform LES simulations. Here in the left picture, we have a run simulation, and we are showing the wind velocity field. Also, in the right, this model, it is an LES simulations. The main differences for this mesh, which was mesh 04, are located at the root wake. This is shown here, where we obtain more velocity deficit when we use run simulations, and also a slightly bigger loads towards the tip. To conclude, I would highlight that the industry right now needs different fidelity tools to face different problems, that the actuator line model is suitable for floating offshore wind turbine interactions, that we obtain using OF2 a computational cost reduction against fully resolved approach, that OF2 can be and will be further improved with actuator line model, and with this set of tools, we will be able to face the floating offshore wind turbine co-design and wind farm control and operation studies. Thank you very much, and I'll be pleased to answer your questions.
Thanks for a nice presentation. The floor is open for questions. There. Yeah, maybe I can repeat it for the online. So, yeah.
So the cost reduction doesn't come because the algorithm is better. It's the same algorithm, and it even performs some calculations. It comes because we have no model, we have no mesh for the wind turbine. So yeah. No, it's computational cost. It's the cost of the simulation. Yeah. Any more? I will look at it. Yeah, thank you for the comment.
Which code was that?
Thank you. I will check it. Okay. Thank you. I will note down. Just in case.
Other questions? We have plenty of time. Yep.
Was simple Smagorinsky for LES, and for runs it was K omega SST. It is not needed because there are no walls, but just to make a fair comparison when we use a fully resolved approach, that is also K omega SST. So that's it. Yes, we have computed also in a more finer mesh that resolves properly the scales, but I wanted to show the differences from a run simulation and an LES simulation with the same mesh. Snappy. Block mesh and then refinement zones with a snappy, yes.